Hi, everyone. Welcome to Foresight Space Seminar Group. It's really nice to see everyone back, and it's really wonderful today to welcome Sara Seager. And we will have Sara here today discussing the Morningstar missions to Venus. So we're going to go quite far out today. I'm going to share a lot more about you, Sara, here in the chat, but it's a real delight to have you on. Thank you so much for giving us your hour of the day. And I'll be in the chat monitoring for questions, sharing more information about the group, and then we will do a Q&A after your presentation. Thank you very much on behalf of the group for joining, and I will see you after you talk. Thank you.
Right. Feel free to ask questions during the talk, everyone. You can put them in the chat, and if they're relevant to what I'm talking about, then I'll answer them. Otherwise, at the end. I'm here to talk to you about Venus. About 5 years ago, I was part of a group that reported the detection of the gas phosphine in the Venus clouds. Now, this detection is incredibly controversial. But what we said about phosphine was that there wasn't any known way to produce it through lightning or meteorites delivery or volcanoes, or no way that we could work on with known chemistry could produce it. And that set off a whole chain of events and led to everything I'm going to talk to you about today. So there's a lot to talk about. I'm going to give the brief reminder to you about Venus. I'm going to talk about the Venus clouds. And that all is the motivation and setup for the main topic, which is the Morningstar missions to Venus. So Venus, you don't have to necessarily read all this, but we sometimes call it Earth's twin because it's about the same mass and about the same size. And anyone who's interested in exoplanets, if there's aliens around a planet, around a nearby star, looking back at our solar system with the kind of telescopes we have, they'll think Earth and Venus are basically the same, because they're about the same mass and size. But it turns out Venus is so different from Earth. It's got some crazy things going on. Its day is 243 Earth days, which is longer than its year. It has no water on the surface and only the tiniest amount in the atmosphere. Instead, it has a massive carbon dioxide greenhouse atmosphere, making its surface so hot, 700 Kelvin, way too hot for any kind of life as we know it. But this whole phosphine thing, it really sparked a new interest in reviving a decades-long idea that although the Venus surface is too hot, just like on Earth, when you go above the surface in a plane or hiking, it gets colder, and so too on Venus. And so the thought is that maybe, just maybe, in the layer of the clouds, where it's the right temperature for life, maybe there is life there. We have life in Earth's clouds. Life gets swept up, little microbes get swept up, and they get into cloud droplets, and they stay there for maybe a few days or a week, and they get eventually rained back down. But this type of life would have to be there forever. What's really interesting about Venus is the former missions to Venus, lots of missions. NASA's Pioneer Venus, which had 4 separate probes, the former Soviet Union's Venera and Vega missions. They left us with some lingering anomalies. And while I don't have time to go through them today, I just want you to know that collectively, we know there's something unusual in the atmosphere. It doesn't have to be life making gases, microbial life making gases, but there's definitely worthwhile reasons to go back to the Venus atmosphere to study the gases and especially the cloud particles directly. Okay, so I've said all this already. But I'm here, the Morningstar missions to Venus. We used to call ourselves Venus Lifefinder missions, but we got pushback from our sponsors, our colleagues, our friends at NASA, and we rebranded to Morningstar missions to Venus. But we're here to search for signs of life and life itself in the Venus clouds. Now, why is the idea of life in Venus's clouds so crazy? I'm guessing most of you know already that the clouds aren't made of water. They're made of concentrated sulfuric acid. That kills all of the life as we know it, actually. And here's actually a schematic of Venus. So we have the surface down here. This is showing you altitude in kilometers above the surface. And if you care to look at the temperature and pressure, you can look at that as well. We're going to focus this talk on this temperate zone in the cloud layer, in this kind of middle cloud layer, between about 48 and 60 kilometers above the surface. There, the cloud particles are 98% sulfuric acid down to about 81% sulfuric acid, the rest water. But this isn't like freely floating water. It's so tightly locked to the sulfuric acid, it's basically unavailable. So that's what I'm here to talk about. And I'm going to jump right into this ideas. Could any life survive in sulfuric acid? My story does go back to the Phosphine on Venus, where I was part of this team that was about to make the announcement. And this was during the COVID summer. Remember that summer in 2020? There was literally nothing to do. I had teenagers at home. I had my 17-year-old, no jobs. The sports fields are closed. So I put him on the Venus project, which, being a teenager, they're digital natives. He finished the problem really quickly. It was just doing some internet research on materials for engineering that were resistant to sulfuric acid. And he pushed to do real experiments. I'm telling you this, you cannot order a lot of sulfuric acid to your house. Pandemic, office was closed. But you can order a lot of little bottles. And so we're outside, set up an outside lab as safely as we knew how. The goal was to gain some intuition. He wanted to experiment with sulfuric acid. I want you to imagine you're that bored teenager in the pandemic summer, and you're in a leafy suburb outside on your front porch. What's the first thing you're going to put in sulfuric acid? Just looking around, a nice warm day. Ant. He put an ant in sulfuric acid. And before I could say, please don't do that, the ant had a seizure and turned to goo in the blink of an eye. So yeah, it doesn't seem like life can survive. And I made a little video for you to take that to the next level, that our DNA, as shown in that cartoon on the far right, has a sugar phosphate backbone. You've all heard of that, even if you're engineers. And sugar is very unstable in sulfuric acid. So if sugar's unstable, our DNA is unstable, the ant is unstable, we're all unstable in sulfuric acid. So I'm going to show you this classic demonstration. That's me in my lab at MIT. There's just a jug of low-grade sulfuric acid. There's, in this glass container, glass is resistant to sulfuric acid. So in this glass container, there's a little layer of sugar. And remember, sugar's a proxy for life. And here's me in the infrared. So now you can see we've sped this up to 2.5 times. Otherwise, it takes too long. I literally just poured it. I just eyeballed it. And you can watch what happens. It's going to take a minute, but look, it's already changing. So that's sugar in sulfuric acid. And now look at the infrared. It's starting to get hot, right? Something's happening there. And let's just wait a moment and see. It's going to, whoa. Basically, what's happening is this sugar is reacting with sulfuric acid, and it's essentially getting dehydrated. There's water rapidly coming off at quite a high temperature here. And look at on the left, look what's happening to the sugar. One of the person I gave a tour, when this was all over, he wanted to smell it smells like cotton candy. It's bad, don't smell it. There's also sulfur dioxide coming off as well. And essentially at the end, you're just left with this black carbon. So if that doesn't convince you our life can't survive, we think this is why the entire community, planetary community, just decided there can never be life on Venus. And that's where we live for a long time. And so what my team has been doing for a long time, this is how it started, my son on the leafy suburb. This is 2 years later when he was a real biochemistry undergraduate student at Worcester Polytechnic. So we're now doing something a little more sophisticated. And what we decided to do 2 summers after that, just experimental summer, was we decided to test parts of our DNA. So the sugar part is not stable, but we took the nucleic acid bases, ACGT, the latter part of the DNA, and we put those into sulfuric acid. And we got this in the early days. I just had this laboratory at home. And what you're seeing in this machine here with my son and I is it's a UV vis spectrometer. So you fill a cuvette about this big and you stick it in, and it shines like UV, invisible light, across that cuvette, and it measures the absorbance of any material in there. And what you're seeing on the right is a plot of the things we tested that summer. These are the nucleic acid bases like adenine, guanine, and some related molecules. And your job is just to look at the yellow curve and the dashed white curve, because those are going from one day to the next. So within 24 hours, you see the exact same peaks. They're a little offset because more of the chemical dissolves a little bit more over time. But look, it's undeniable that whatever started in there is the same the next day. And we immediately knew right away that these nucleic acid bases are stable. That's not a standard of proof, but it's like an easy way to get a handle on how it's going. And so how it started, how it's going, I had to train at MIT to use the NMR, nuclear magnetic resonance, and actually do this all legit. I'm not sure how much detail people want, but now I've got a laboratory and we're doing a ton of amazing experiments. I'm going to maybe walk you through 1 or 2 of them that I think is really germane to convincing you. I'm sure you don't need convincing that it's worth going to Venus. But we're doing all of these experiments to demonstrate to our would-be sponsors that there's something there, that there could be life, not that there is life, but they might be life. So I've just picked a couple of many experiments ongoing here. And the first one is about our 20 biogenic amino acids. So we require these 20 biogenic amino acids. Our body makes some of them. And we took all of these amino acids, each of them, and put them in sulfuric acid. And what we found was that they're all stable with one exception, although some of them get chemically modified. And I just thought, if you don't know what this is, let me walk you through it. This is showing you intensity. And this x-axis is called like a part per million chemical shift. And this is coming from nuclear magnetic resonance, where you put your molecule in the sulfuric acid, leave it for a day, a week, months, put the tube into the machine. And what the machine does is it's a very strong magnetic field, and it sends a radio frequency pulse and essentially excites the nuclei, the spin states, and then they go back down. So it's not like your traditional spectrum that we're used to, where light is exciting electrons or rotational vibrational modes, but it's actually radio frequency pulse exciting these nuclei spin. So what you're seeing here is 1, 2, and 3 correspond to carbon atoms. And if you're not a chemist, or you've forgotten chemistry or never studied it, I hate it because the chemists draw molecules. You can see oxygen, hydrogen, nitrogen, and they never draw the carbon. Like, it's so crazy. They literally never draw it. You're just supposed to know it's there. But here we're showing you 1, 2, and 3. But if you didn't understand anything I said, what you can understand is that there's 3 overlaid lines each of here. One is white. That is our molecule in concentrated sulfuric acid. Blue, our molecule, this particular molecule, in 81% concentrate sulfuric acid, the rest water. And the red dashed line is just in water. And you can see they're all overlaid. They're all basically identical. And that is the evidence that the amino acid is stable in concentrated sulfuric acid, because we measured this within 1 day. We measured it a week, 2 weeks, 2 months, 4 months. And these same carbons, they're always in the same place. They never change. If this was actually broken down, you just wouldn't see any peaks. You'd see a lot of minuscule lines, like the breakdown products. You wouldn't see anything. And so I wanted to show you this picture. These are the 20 biogenic amino acids. And you can just, like, at a glance, you don't have to understand the details, but you can see where it's blue. That was how this particular molecule got modified. This blue here, this got modified. This one was unstable. The red's how we think it got modified. So it's actually remarkable, because although we have 20 biogenic amino acids, there are like 700 known amino acids out there. There are probably many thousands possible. And it's amazing that this very most fundamental building block of life is essentially stable in concentrated sulfuric acid. I'm not going to go over this detail, but this is the same as, I'm going to just take a miniature break here and answer a couple of the questions that are here, because they're very relevant. One question, and I get this question a lot, is about extremophiles. Could extremophiles survive here? And the answer is no, because our DNA cannot survive. I think I made that as clear as possible. The sugar in our DNA will fall apart, and so our DNA cannot survive. So the problem is that the sulfuric acid, it's orders of magnitude more acidic than the most acidic environments here on Earth. Have I considered how rapidly this kind of biological adaptation can take place? No, I don't know. I don't know the answer to that one, but we can come back to all that a bit later. So our goal, by the way, is to construct a DNA-like molecule. So not our DNA, but swapping out parts. Because I want to be able to take that to the world, and especially the private sponsors, and be like, look, there's a DNA-like molecule that is stable in concentrated sulfuric acid. There's an informational polymer. And it doesn't mean there's life there, but it motivates the search for life on Venus. So I hope you all agree with that. And we don't have DNA yet. We have made a milestone in that direction of swapping out parts. I can answer this more later if you want to know more details. But suffice to say, we're making good progress. I wanted to share one more thing on this with you, and that is this one more thing in the experimental side, and that is these vesicles. You know, when people are working on the origin of life in water on Earth, they take lipids that have a polar head and put it in water. And what happens is the lipids line up, pointing their polar head outward to interact with water. And in the right conditions, they can form spherical vesicles. And there's some people who, want to promote one path for the origin of life, that vesicles formed first, like a membrane that could be like a very primitive step in the formation of cell membranes. So we asked one of our colleagues, Daniel Dusevich, to try this. And he worked in Jack Shostak's lab, and they stained it with a dye and put it under the microscope. And they found not only that these lipids are stable, but they do form vesicles, spherical vesicles, that also form more complicated shapes. You can see it looks like it's kind of breaking off here on the right. It's like a longer thing that's breaking off into its own little vesicles. And in the origin of life on Earth, they like this because they're like, oh, it's kind of like a first step in cells, not reproducing, but yeah, replicating or some room for it. So we have a lot of stuff. I'm just going to flash this up. I check if there's any more questions at this time. And you can, there's just so much work that we're doing. We're trying to get other people to do it. We're trying to attract people who do quantum ab initio simulations with the computer to help guide our experiments, because we've done a lot of obvious things and now we're getting stuck on some harder things. We have found some proteins are stable. We're trying to find, not big proteins, but little peptides. We're trying to find if they fold or not. And we're getting a bit stuck, so we're going to need experts in computational chemistry to help out. Okay, any questions on this part? Okay. So what are we going to do about all this? We're trying to go to Venus with a series of small focused missions. We call ourselves Morningstar missions to Venus. So I'm going to give you like the whole story of how this originated. It originated because during the time of the Phosphine announcement, I gratefully and thankfully got a small amount of seed funding from the breakthrough initiatives to study what could be missions to Venus that could be focused on finding signs of life or life itself. And this was all during the pandemic. And I handpicked a core group of people that were willing and interested and wanted to work hard on this subject. I actually only had one person, David Grinspoon, who knew anything about Venus. And I hope you find this part funny. It's hard to do this over the internet, but I also excluded any cranky older people because I wanted to have like fresh voices, fresh thoughts, let every voice be heard. So we met a lot weekly. We had two key people from the breakthrough initiatives, Pete Warden and Pete Klupar, met weekly. And then about 2 or 3 times a year, we'd open it up to the whole Venus community who are doing more traditional, managed to get Da Vinci and the other missions. We were not traditional, but we let everyone join. And it was incredible. We had a great time. We had to really start from scratch because our knowledge base was so limited. And I'm now going to walk you through what we decided to do and what is happening and what is hopefully going to be happening. But before I get there, we're excited that, okay, I don't know if it's true or not, if Phosphine triggered all these wonderful things. I literally had people call me and thank me from a bunch of places. It's not like we did it on purpose, but Phosphine gave Venus the attention it deserved. It deserves. And we do hopefully have a bunch of missions going to Venus. So there's the European Space Agency Envision, it's an orbiter. NASA's Veritas, an orbiter, and Da Vinci is going to go with a parachute down through the atmosphere. None of these missions by NASA or ESA plans to interrogate the cloud particles. And if there's life, it's going to be associated with the clouds where there's liquid and where they can be protected from the harsh outside atmosphere. Other missions are being planned. India, China, and other countries. And hopefully we'll get back to a heyday for Venus like we had decades ago. So we came up with a plan with 3 or 4 missions. And these missions are, we just like to describe it as small, medium, and large, short-term, medium-term, long-term. Now, one of the people who attended our meetings, and we were really open, we didn't restrict people attending or not attending, was Richard French from Rocket Lab. And there came a time, like maybe 1 or 2 years into our, formulation, where he told us Rocket Lab wants to go to Venus with the Electron rocket, and they would love us to join as the science team. So we started working closely with Rocket Lab. We still work closely with Rocket Lab. And we did come up with a mission. We were allocated 1 kilogram. So if anyone works in space, that's not a lot, but we do have more miniaturized things going on. And here's kind of a picture of where we're at right now. That's me in my lab holding a 3D printed version. That's like full size, real version of how big the probe is. And here are the folks at NASA Ames who generously gave us the heat shield and the tiles on the upper side. So this is the real one. This isn't like a model. There's like a protective tape, which is what makes it look orange. But you can see this is the probe. So to get it in your heads, the rocket will launch. It will release the spacecraft, which is the cruise vehicle. The cruise vehicle will go to Venus. It will open up and drop off this probe. And this probe will enter the Venus atmosphere. The cruise vehicle is also going to enter, and but this probe will enter. It's remember, short-term, cheap mission. It doesn't have a parachute. This entry vehicle, it usually pops off with a little drogue chute, and usually you get rid of it. We're not doing that because, it's called a pilot parachute because it's cheap mission. Now, if you look closely, you can see this hole here. Can you see the hole where my cursor is? And so I can now move on and tell you a little bit about the instrument. I'm going to go, I had a different order for this, but here's like a schematic of the probe. And you can see on the right, it has like inside, it's got a battery, a tiny bit of ballast, and it shows you a few other things going on. The antenna is at the top. Inside the probe is this pressure vessel. I forgot to say that. And inside the pressure vessel is our instrument. And this is showing you a schematic of the instrument where it's going to shine a laser through a window in the instrument, and then it will go through that hole in the outer probe shell, and it's going to interrogate the cloud particles. Now, one thing is, as this probe is like racing down through the atmosphere, we want to focus outside of that airflow, so we don't want to get contaminated by any particles that might be burning off of the heat shield. And that's why it's showing you out here from the capsule. And we're going to do a couple of different things. We're going to look for autofluorescence. I just put this picture here to remind you what autofluorescence is. Look at these green eyes from a special droplet that was put in for a test. You can see the white t-shirt lighting up. It turns out that organic molecules are highly susceptible to fluorescence because they often have shared electrons, like a ringed molecule. Oftentimes, the carbons are sharing electrons, and they're very easy to excite and drop back down. So in the laboratory, we carried out an experiment with a lot of different wavelengths of excitation and a lot of emission like basing on detecting. And you can see this plot here. It's not exhaustive, but this is some of the experiments we did. And because it's a small instrument, it's only 1 kilogram, we had to pick, like, where do we want to be in this space? And we picked a region that not only looks like it's, the chemicals may be there fluorescing, but it was also based on what's commercially available in terms of the laser itself. So we've got a laser, we have a detector, and that's going to be in the probe. And we're looking for a second thing as well. We're also measuring the backscattered polarized radiation. It turns out that in the past, people have measured backscattered intensity. We're adding polarization to that. Each particle in nature, no particle in nature scatters equally in all directions. So if you go around shining a laser at things, there's a pattern to how the light scatters. And you already know this because of rainbows. A rainbow on Earth means water is concentrating the light. And if you ever have polarized sunglasses, and if you turn them at the rainbow like this, the rainbow will literally vanish, actually, because you only see it in one, And so because of polarization. So we're going to Venus. We're going to interrogate the cloud particles. We're trying to confirm past missions have identified the different size distributions, the index of refraction, which we can get out of the polarized radiation. And we're also trying to confirm it's not pure sulfuric acid, that as before, some of the experiments showed, the in situ measurements showed that some of these particles may deviate from pure sulfuric acid, which is interesting to us from the life viewpoint. Here's, the parts. We have a flight instrument. We have a flight spare, just for you to see that. Okay, so we have taken our flight spare and tested it on a drone in Hawaii. It's kind of larger than a drone, like a light aircraft. That was what you see here. We went to this farm where they let you go for experiments. And here's the light aircraft on the table. It launched from this kind of complex bungee system. And on the right at the bottom, you can see the instrument. We were a bit heavy for this setup. And so it's a bit, that's our instrument there. And our goal was, because the volcano's been erupting, is to fly on the outskirts of the volcanic fog called VOG. You're not allowed to fly right over that volcano or anything. But the idea was to test out our instrument, to test out our data transmission protocol and things like that. And it was successful, I'd say. We're We have one more. I wanted to give a shout out to Professor Chris Carr from Georgia Tech, who got outside funding to do this project. So one more slide on this mission, if you just wanted to see what's happening. This is showing you altitude above the surface in kilometers, and this is time from entry. And you want to be looking at this black curve here. And if you can look at it closely, you will see it slowing down from its own drag. And because there's no parachute system, this will have 5 minutes in the Venus clouds. We will be able to continue transmitting data below the clouds until our probe interior becomes so hot that most likely the electronics will fail and will end our mission. So that concludes like this part of the Rocket Lab mission to Venus. Any questions on this part? Okay. So in this mission, I'll just give you an update. We have like our flight instrument is completed, our flight spare is completed. We may do a few more tweaks. We'll probably go back out to Hawaii or somewhere else to keep testing the instrument. We've been working on our algorithms. We're trying to decide what data we're sending back because we have very limited direct data to Earth. And so while Rocket Lab is moving along with you saw the probe and they've got the pressure vessel and everything else, I've turned my attention to the next missions. So our next mission, we're working on 2 missions in parallel. We're in what we call pre-phase A. We're trying to move these far enough along so that they can be fundable. The whole private funding world, it's very different from NASA. So I've been investing literally my own discretionary funds, which are rapidly dwindling in these missions. Okay, I'll just say a few words about this. I actually have way more slides, but I didn't want to overdo it too much. We really want to find complex organic molecules on Venus. Our first mission will go to Venus. It will see fluorescence. We're confident of that. We'll measure the backscattered polarized radiation, but it's very ambiguous as to what's really there. And that's partly by design because it's a small mission. It's very focused. It's low cost. And so now the question is, what is evidence for a sign of life? We want it to be a very complex molecule, but where you draw that line between a molecule that's just complex because it grew and got added onto in the atmosphere itself, or it's so complex that only life can make it for life's purposes. Nobody knows where to draw that line. So we're trying to use our best judgment. And one of the common ways people study molecules is mass spectrometer. So I don't know if everyone knows what a mass spectrometer is, but these are difficult, very difficult. Most of the ones been sent to planets. They ingest and pyrolyze and then analyze. That's challenging because you kind of lose the original parent molecule. Now, in a mass spec, you lose the parent molecule anyway because it gets fragmented from the ionization. But we didn't want to do that. We wanted to, it made our life really hard, but we want to go to Venus with a mass spectrometer that very gently puts a charge on without pyrolyzing, without completely fragmenting the molecule into a million pieces. And we've been working on that. And we're working with a mass spectrometer called Origin, and it comes out of Bern, Switzerland. They've got one on our Artemis going to the moon, and we've been working closely with them. And it's quite complicated because it takes a long time for one measurement or one set of measurements, because essentially you have to collect and deliver. You have to collect the cloud particles, you need to condense them. We need to get rid of the excess sulfuric acid, and sulfuric acid is a very high boiling point, so we need a low pressure chamber. And then we have to deliver the material to the instrument. And then the instrument basically has to be vacuumized. And so the whole cycle to collect, condense, evaporate, deliver, it's not only really complicated, so if you work in space, you don't like complexity, but it takes time. And so that's what drives the requirement for the balloon, because you don't have enough time with the parachute mission to cycle through collecting the cloud particles and everything. So we're still working on this. We're kind of bringing it all to pre-phase A. The Swiss have been very generous with their time, and we've met with them and discussed interfaces. And we also have our balloon vendor, Maxim de Jong here. That's Maxim, that's his daughter, Signori, who works at the company full time. That's myself. There's some other team members here. And here's a balloon he developed before. We'll have time during the Q&A. I forgot to show you the latest photos, but he's developing a full-scale, high-fidelity balloon for our pre-phase A work. And I'm really excited because I'm about to get the half scale that I'm going to get. And next time I could literally show it to you. But we're all heading to Ottawa next week for the Explorers Club. They're having their summit in Ottawa for a full day on Saturday. And we're going to be bringing it's 2.5 meters in diameter, the half scale balloon. I actually do have a lot of technical slides. I decided not to show it to you because I have a topic I'm more excited about, which I'm going to talk to in a moment. And before I get there, I see a question in the chat from Arushi Nath. Hello. She asks, as temperature on Venus decreases, do you envision future missions moving beyond descent towards the aerial drone-like flyers that could remain aloft? I imagine the balloon remaining aloft. The balloon can remain aloft. We're not here to try to last forever and do a million experiments. We're here to just get what we need and be done. So we're thinking of 1 week or 2 weeks. Okay, so I'm going to talk about a simpler mission now. And so this is our second mission we're moving forward. This is a parachute mission. And at the bottom, this isn't supposed to be 10 meters. It's supposed to be 5 meters in diameter for the parachute. And attached to the parachute would be this little probe here. On the left, it's showing you what would be the entry vehicle. So this is not like in the Rocket Lab mission to Venus. That's not the whole thing. That's going to go away. There would be like a little, I was supposed to say pilot chute attached to the top that inflates as it's descending. And that would pop the whole thing open. And this entry vehicle shell would go away. And inside, there'd be a parachute, and there would be this little ball-like, circle-like structure that's a pressure vessel. And this whole parachute will descend. It could last for about 35 minutes. It depends on the mass of the probe and the width of the parachute. I've got to just fast forward and see what order I put things in, because I might have put it in the wrong. Okay, so here's like a schematic on the right showing you the altitude above the surface in kilometers, entry and deceleration, where that pops off the shell. We may have some mini probes deploying. And then you see the parachute deploying, and we'll be taking measurements. So we had a really exciting summer because we decided that, there's 10 steps to getting this thing done, more than 10. But we took our very first step. And that was an MIT Aeroastro master's student, Claire, designed a parachute based on past ones that have gone to Venus. And this one won't survive in the atmosphere, but she laser cut the polyester material. She sewed it on the sewing machine. And the goal was to test this here on Earth in our atmosphere. So she got this whole thing together. And she also found out so being an astronomer, I love amateur astronomy. I work a lot with amateur astronomers. I somehow didn't know there's amateur weather balloon people. And they launch balloons. And Claire found our local amateur balloon society, the New England Weather Balloon Society, and they helped us launch. So here we are. This is their facility in Natick, Massachusetts. It's about half an hour away from MIT. And we're filling this weather balloon with hydrogen. The goal is that it's going to go up and expand to match the pressure as it rises, the dropping pressure, and eventually pop. You want it to pop. And attached to this balloon's our parachute. And we also have a payload, which I'll get to. So there's a couple of fun facts here. As long as you're under, I want to say it's 12 pounds, you don't have to register with the FAA. You just let them know that you're doing this. And our Weather Balloon Society contact took care of that. They have really nice software that they keep checking to see what's a good day, because it can't blow out to the ocean. That's not allowed. And you also want to make sure it's going to land somewhere in public property. So the day of, we would keep checking the software to see where it was going to land.
That'll be dull. My mass fast 3.
So here we're launching. And you see the orange is Claire's parachute. And we have our little box of sensors, which I'm going to tell you about in a moment. And there's also a big reflector, just like a simple aluminum foil reflector, I guess, for planes and everything to see. So I'm just walking you through this little travel dialogue here. What happens is there's a software that the weather balloon people use, and they also have an amateur radio tracker. And their car has an antenna like on the top, just for better bandwidth. And so we're just constantly checking the app to see it's all getting registered where our balloon is. We're over here somewhere, and it's supposed to land here in a state park. Only they gave us a little bit of extra hydrogen because our payload was heavier than they're used to, and we went way higher than we were wanted to, we went to 70,000 feet in Earth's atmosphere. Cool, huh? Here's a picture before our GoPro failed because it was too cold. And yeah, that's a picture we took from our balloon. So what were we trying to do with this? One thing was to test Claire's parachute, and great job to my student because it deployed and it came down and it matched the velocity that she had predicted based on the design and drag coefficient. My favorite part of it wasn't anything I've told you yet, but it was this little box that actually went to 70,000 feet. It says Morningstar missions to Venus. What's on here is 32 sensors, 30 on the outside, and we had 2 on the inside. And these sensors are temperature, pressure, weather, but they're a stand-in for the parachute mission where I'd really like to send 10,000 miniature molecular sensors. So remember, one step at a time. And this is an undergrad project. I'm also proud of my undergraduate student, Eddie, who got this whole thing done, and it worked. You know, just a week before, he shorted out his entire project due to poor soldering, but he got it done, and it made all the measurements. Everything worked. And so this in itself, of course, this is a long way from being ready for Venus, but I just wanted to share with you some of the excitement of everyday engineering. Here's that thing I showed you, the sensors. It's in a cooler. Fortunately, we landed in a tree and not in the adjacent swamp because water would have destroyed the sensors. We didn't send data back to ourselves. It was all recorded on an SD card, okay? And so, yeah, here's the SD card plugged in. Sensor's still working. So it was a very exciting summer for us. I haven't told really many people about this, so I'm going to keep it brief. Basically, what I want to do is I have a little, okay, this is still kind of getting formulated, but I'd like to send a probe I showed you with patches on the outside, and that these patches can be covered with miniature molecular sensors. And we're working to find which sensor and do more demos and develop things in the laboratory. And one of my favorites we've come across this summer are carbon nanotubes. And what these carbon nanotubes are, they're actually highly conductive. But what people do is they put a defect on it. So they add a molecule to it. And when the electron configuration changes because of the added molecule, the conductivity changes. So I want you to imagine a molecule added on. And now we have our gas or our sulfuric acid hitting our sensor. And when and if that molecule added on matches the right piece that it's going to bind to, it changes the conductivity again. And so you essentially have a chemoresistor. And that's what we're pursuing right now, to put as like a new miniature molecular sensor to go to Venus. And I'll spare you some of the details because I want to leave plenty of time for questions, but we have many colleagues we're working on this with. This is just a place in New York City that I took my student Eddie to this summer, just to show you they're designing these nanotubes with the defect molecules and testing them literally just in the lab. Okay, let me think of where I'm going with this. Okay. So if you want to know more, you can go and read this report. When we used to before call ourselves the Venus Life Finder mission, we wrote this 120-page report. We also chopped it up into actual published papers in MDPI Aerospace special issue from 2022. Okay, I'm going to summarize now. Venus has many long-standing mysteries. Mostly these anomalous gases. Many of them have been measured directly in the atmosphere by probes from nearly 40 years ago. I hope I've convinced you that sulfuric acid clouds are not sterile to interesting organic chemistry, based on new laboratory experiments. We're doing the laboratory experiments to motivate missions to Venus, yet all these experiments have taken a huge life of their own. I hope we're entering a new era for Venus exploration, where we can carry out a series of very focused, largely privately funded, but public funded missions to Venus. They'll be complementary to the bigger missions, but they're needed to carry out this pursuit of looking for signs of life or life itself in the Venus clouds. Thank you very much for your attention.
So cool. I can't believe this all worked out. What a busy, what a busy year, and so much like amazing engineering done on the fly and then it all working. It's really cool to see, very inspiring. Okay, we have a bunch of questions already. I'm just going to start, and then I will have perhaps a bit more speculative questions in the end if we have time for it. But for now, we might start with Micah, who has his hand raised.
Okay, and after that, I'm going to go to Stephen's question that he asked online.
Yeah. I know there's a lot that Stephen asked in the chat. We won't forget about you, Stephen.
I know your work is focused on kind of easy, cheap, short-term missions, but I'm just curious what your thoughts are on what would it take for us to actually bring back some of the atmosphere from Venus or even some of the material on the ground, what would that look like in the far future when we can do that?
And that's our mission number 3 that we kind of dropped. We did get a NASA NIAC phase 1 to study it. The thing is, let's talk about the atmosphere first. We could go to the atmosphere. We're fairly confident we can develop a way to collect cloud particles, to collect the atmosphere. But the problem is then from a balloon platform, let me back up. You have to carry a large mass because you need to get from your sample collection from the balloon back up to orbit. So essentially you need to have a mini rocket on your balloon. And that is the biggest challenge right now because it has to be pretty massive. We're not sure how massive, hopefully like a ton. I mean, a ton is huge, right? Hopefully it's not a few tons. And so how you can do all of that, meanwhile, your balloon and this gondola is probably spinning and the winds are really strong and you have to be able to point to get where you need to go in orbit. And that's kind of a really sticky point of figuring all that out. Now, that said, there are people on Earth who were for a while doing something they called raccoon. So at least an Earth is more simple and our Earth is more friendly in the atmosphere, but we're hoping other people can move this technology forward at some level before we return to this. Now, people have worked on this before, and I do think there's even another NIAC now about going to the surface. And in some ways, maybe the surface is easier because you're not flopping around wildly in the atmosphere. I forgot to mention that a massive balloon also, as the entry vehicle pops out and your balloon itself has a parachute and is descending, it also has to inflate rapidly before it gets so low it can't rise. So we did actually make a new proposal, and Maxime de Jong, our collaborator who's building the first balloon, he had ideas for how to test that because you have to rapidly inflate a giant balloon. So it may seem easier to go to the surface because you don't need the balloon and you don't need to point in a crazy environment. But the surface is so hot. I mean, there are people who love to work on electronics that can survive at high temperature, but you don't have very long. You've got to go to the surface and land, scoop stuff up, and then you have to launch and get back to space. So yeah, it's definitely really hard, but I think it's the only way we're going to prove there's signs of life anywhere is by sample return. Okay, so I'm going to just quickly turn to Stephen's question. Might the unknown atmosphere absorption phenomena be caused by pyrolysis of organic molecules like polyaromatic analogs from recent millennia dehydration of hydrogen precursors? Love the question. It doesn't have to be pyrolysis because one of our team members put simple organic molecules like formaldehyde in sulfuric acid. And admittedly, they heated it a bit, but they saw evolution of organics like all the way to aromatics. And so they think it's their proposal, just like what you said, that the unknown UV absorber is aromatics. They're strongly absorbing. And that's what's doing the job, not from pyrolysis, but just from forming from reactions in sulfuric acid.
Would that account for the spectrum that you see?
They say yes. They've done some measurements in the lab to show that. But honestly, it's probably a lot of things, We tend to get into camps. Like one camp is, hey, it has to be these iron particles. One camp is going to say it's aromatics, but it could be a combination of all of the above. Yep. Potentially with these mini molecular sensors, we could go and identify what it is if we're smart enough to design the, puzzle matching piece to what we think is there.
Would you be open to taking another question from Micah?
Sure.
I was wondering, why do we look for life that looks molecularly similar to us rather than something that is self-replicating but maybe doesn't look like us at all?
Looking for something that looks like us in the sense of we're looking for complex organic molecules.
Like why organic molecules instead of something that's maybe we would consider inorganic, but on Venus maybe it functions similar to how organic molecules function in water?
I think that, okay, let me just think about how I can best answer that. First of all, I do appreciate the question because we tend to be very terracentric, even when we feel like we're being expansive. But there's really not a lot of, when you just have inorganic chemistry, like non-carbon hydrogen molecules, there's just not a lot of them out there. And I feel like life needs to use all the materials that are out there. We could take a step away and maybe talk about something a bit in between, like people love to talk about silicon-based life, maybe. But I don't think I've ever seen anyone even be able to go to like inorganic molecules making up biology.
And just to build on that, just very briefly, would silicon-based life hypothetically work better in Venus, or does it have the same exact problems in sulfuric acid?
Hypothetically, it might work better. One of the things in what I know people love silicon-based life. The reason why I dropped it from my attention entirely is because silicon and oxygen, anyone know what that is? Silicates in rocks. It's kind of like I always think about, and sand, yeah. Sand, and we have SiO in rocks. Like, what happens if you eat sand? Like nothing. I mean, okay, like it just is locked away. It's like a super glued together when you get silicon and oxygen. So it doesn't really make sense for life to use silicon here on Earth because it just really, I can't break apart. It could do a little better in sulfuric acid. So there's one idea there. Maybe you could imagine substituting some carbons for silicon, but it's unclear.
I have perhaps a more speculative question, but you feel free to. Oh, no, actually, Anand, you go first. I don't know, Sarah, if you want to read the question from the chat. Otherwise, I can read it out.
Of course, there's pros and cons. The pro we went in with was we just want to do a small focused mission. We have a singular goal and we need to get to our goal. In NASA, because, there's so many great ideas, but we can't fund all the great ideas. So typically in government, everyone has to work together. And it has a bit of a negative snowball effect because then the mission gets bigger and then it gets more complicated and takes longer. So we went with the pro, and that pro has been there. I want to say one thing that's been absolutely a dream, but it could also happen in the government as well as in private, was working with Rocket Lab and having, in the jargon parlance of the single vertical integrator, I don't know exactly what the words are. So instead of having like different pieces where we or you or someone has to manage them all coming together, there's like a single, we are a single instrument. I'm responsible for the instrument and science team, fundraising, managing, delivering. And we have a wonderful instrument team led by Daryl Baumgartner at Droplet Measurement Technologies. But ultimately, I have to take full responsibility for all that. But because we're just a single instrument and then a single other, the space company, it's been an absolute dream. And if something goes wrong or there's a bottleneck, it's managed internally at the space company, and it's been amazing.
Yeah, that was the answer to the question of benefits.
Oh, I do want to say, Oh, go ahead. I just want to answer Rishi. Oh, my student was an undergraduate. The one who did the parachute is a master's student. And then it was an undergrad student. However, the weather balloon, there's a lot of high school students. And we did take a Geiger counter made by a high school student because it had failed on a previous mission, a previous one of their balloon launches. So we did have a high school student experiment. But I bet that Arushi is one of those high school students who could easily participate in building something here.
Maybe they're very young and junior and fresh looking on the photos. That's why. Okay, wonderful. I have a few more speculative questions, but again, anyone can interrupt me by just asking a question in the chat or by raising their hands in the last 6 minutes that we have here. One of them would be that, in some sense, Venus is one of the more easier planets to get to, depending on, how you look at it. But do you think on a more speculative sense, we will ever get to do a human flyby? Why are we not? And, how might Starship affect like future missions in the interplanetary sense, not just Venus, but also, other planets that are around. So basically, if you put your speculative hat on in the next few years, what might we see around Venus?
Who here would love to go around Venus and come back? It'd be fun, yeah?
If you can come back, yeah.
Yeah, I mean, you just orbit it. I mean, some people do talk about further training for humans on long space flight missions. Instead of going to space station for a year, let's go to our next level and maybe do a swing by Venus, or maybe you could swing by Mars and Venus without landing and then come back. There are proponents of the humans to Venus. There's another group out there who will say, maybe there's a future. I mean, maybe there's a future with large inflatables and you go to Venus, not for your vacation or to live. So instead of imagining going to Mars and like living in a cave, or like an inflatable Mars, in the Venus atmosphere, the surface gravity is almost the same, so you don't lose that. The pressure and temperature, like in the cloud layer, is the same as here on Earth. So, there's those folks as well. I'm not sure if that will happen. I could see someday having tourism that just goes and orbits a planet and comes back. But I don't really see, I think it would be much harder to convince people to go to Venus. Yeah, if you're not just orbiting it and coming back.
All right, awesome. It also seems in general you have such a unique journey through education, science, space projects. You have so many really fantastic collaborations. Could you say a little bit more to that? Is that yeah, it's, in terms of our presenters, that has been a very rare background so far. So it's really awesome. How did you get to be so experimental and collaborative in your work? And what have you learned from that?
Okay, sure. I think it's like a lot of things. Sometimes you have a project around your house and you just, if you do it yourself, it'll be harder, but it'll get done the way you want. But since you asked and we have a few minutes, I definitely can, there's a negative thing. So I think I should, in all fairness, I just want to say it. And I'll just try to summarize this very briefly. The whole phosphine on Venus incident, how many of you, lived through that or paid attention? It was really crushing for me personally. And it's not because of phosphine on Venus. Like, it is very controversial. That's part of being a scientist. But I just want to tell you why it was so upsetting. Because my whole life I've worked on exoplanets. I'm one of the founders of the field. I invented the main way we study exoplanet atmospheres today. And our whole goal was we're funneling towards finding signs of life in exoplanets by way of gases that don't belong. I should almost ask Arushi, who I know, by the way, she's from my hometown of Toronto, not to listen to this because I don't want to discourage any young people. But if we're fighting about this phosphine on Venus and methane on Mars, like, what's going to happen when we find a sign of a gas we think is a sign of life on an exoplanet? Like, just, I only have a minute here, but it's not pretty, okay? And we'll just say none of us are getting any younger. Like, when you look at your horizon, it's very challenging. We need to, I think it's going to be impossible. We can find maybe signs of life candidates. We can call them whatever we want. So I had to take a break and I had to pivot. So it wasn't like, oh, I do this, I do that. I had a really purposeful reason for turning my attention to Venus. So I had a ripple in space-time, or whatever you want to call it, like a personal or professional explosion. And I had to really think carefully what I wanted to do next. So I still work on exoplanets. I do a lot of work there, but I turned my attention to this. And I also got to, this is also really important because it's kind of like investing. If you're young, they tell you invest in something risky because you'll get compound interest and it will accumulate. And if you're a lot older, they say don't invest in something risky because you're going to need to retire and you need your money. It's kind of the opposite in science, I'd say in engineering. When you're young, you can't take too many risks because you need to get some deliverables to get your next job. But as you age, you should change that risk profile. And as you have less time left and hopefully secure accomplishments behind you, you can take risks. So I had a combination of, a kind of, wow, the thing I set out to do might not work. Not because of anything we did in astronomy, but just because of, what nature provided. And then we have to now pivot. But then the whole journey just got so interesting. Like, one thing led to another, and one discovery in the lab led to a new discovery. And I was also surrounded by people. Well, I'll have to give a bit of credit to MIT here. The environment allows for it, like, it enables out-of-the-box thinking, and you have enough people around who will join that.
Fantastic. Thank you so much. If people are super inspired by your work, which I think many here in this seminar and beyond on YouTube are, like, where can they find out more what's going on your horizon? And then
I think you did put the links in the original on the page. It's morningstarmissions.space, and you can check out my website. I don't post too much on social media, but you're welcome to follow me there in case anything changes.
Thank you so very much. It's really inspiring. Thanks for the work that you're doing and for sharing it with us. Thanks everyone for joining and for your great questions. Thank you.
Bye, everyone.